In this video, we're going to use finite sums to estimate the area under the graph of a given function. And in this problem, the function is x minus 4 quantity squared. And we're going to look at this function between x equals 1 and x equals 9. And we're going to estimate this area using three different methods. Each of these methods uses rectangles. So we're going to estimate an area under a curve using rectangles in three different ways. So a good place to start is to let's sketch a picture of what this region looks like. You can use your graphing calculator for this if you like, but this x minus 4 squared, that's a parabola opening upwards, and the minus 4 shifts it 1, 2, 3, 4 units to the right. So the vertex is going to be at 4, 0, and it opens upwards from there. So something like this, and we don't need a perfect picture, just something that gives us the idea of what we're looking at. And we're going from 1 over on the left over to 4, 5, 6, 7, 8, 9 on the right. So something like this. And it looks like it's in two different parts, this region. But that's because it hits 0 in the middle, or at x equals 4. So we want to find the area of this non-rectangular region, but we're going to approximate it using rectangles. And so for the first two methods, we're going to use 4 rectangles. First, we're going to do a lower sum with 4 rectangles. Then we're going to do an upper sum with 4 rectangles. And then the third way we're going to do it is the midpoint rule with 2 rectangles. So if we're using 4 rectangles in these first two parts, we want to divide the number line from 1 over to 9 up into 4 equal parts. And so to figure out the width of those intervals, I'm going to look at the difference. 9 minus 1, that's a distance of 8, and divide it by 4, because we want to divide this into 4 rectangles. This is 8 over 4, which is 2. And this quantity is called delta x. That's the change in x. And that's the width of our 4 rectangles. So we're going to go from 1, and then we're going to go over 2 to 3, over 2 again to 5, and then to 7. And now we know what the bottoms of our rectangles look like. The first one's going to go from 1 to 3 and up from there, 3 to 5, 5 to 7, 7 to 9. But we don't know the heights of these rectangles. And the height of each of these 4 rectangles is determined by the method we use. The lower sum means we're going to use the lowest possible, the shortest height for each interval. We're going to look at the lowest value of the function on each individual interval. So for the first interval, from 1 to 3, we can see that the lowest value happens at x equals 3. So the height of this rectangle, so this rectangle is going to look something like this. And the height of the rectangle is going to be f of 3. We're going to evaluate the function at 3 to get the height. The second rectangle, which has a base that goes from 3 to 5, the low point in that region is 0, which happens at x equals 4. So the second rectangle is actually going to be flat and have 0 area. The third rectangle, the height is going to be determined by the value at x equals 5, because that's where it's the lowest. And the fourth one is going to go up to a height of, the height here I'm drawing, the y value here is f of 7, will be the height of this one. So to estimate the area of the yellow shaded region, we're going to add up the areas of these 4 rectangles. The formula for the area of a rectangle, base times height. We can find the area of each one of these if we know the heights. And the heights are going to be determined by the function. So in order to compute this, I have to know what is f of 3, f of 5, f of 7. And we can plug those into the function. For example, f of 7, 7 minus 4 squared, that's going to be a height of 9. But we can also use our calculator for this. And just want to show you, this is a shortcut for some problems. If we have a function that's a little more time consuming to compute, we can go to our calculator and put in this function. X minus 4 quantity squared. There's our function. And if we want to, we can look at we could use a graphing calculator to graph this. We know what this looks like. There it is. But another feature of this calculator we can use is the table tools. And I'm going to go to table set first, which is above the window button. So second window takes us to our table setup. And the table right now my table starts at 0 and has a step size of 0.5. I want to change that. I want to start at 1 because my interval starts at 1. And let's do a step size of 1 also. And now when I go to my table, which is above the graph, I'm going to hit second graph. I'm going to see the table. It gives me all the values of my function all at once. So we said just a moment ago, f of 7 is 9. This shows me that and shows me all the others. And we can see these are all perfect squares. So we could have done this without the calculator, but this is a shortcut if you need to compute many values of a function all at once. And once we have this table in front of us, we can, this table is what we really need now to compute these estimates. So for the lower sum, the lower sum we said already. So the lower sum is going to be the area of these 4 rectangles. The area of the first rectangle is the base times the height. The first rectangle has a height of f of 3. So I'm going to use 1 for the height. And the second rectangle has a height of f of 4, which is 0. It's a flat rectangle. The third rectangle has a height of f of 5. And the fourth one has a height of f of 7. And so my 4 heights are 1, 0, 1, 9. So the first rectangle has a height of 2 times 1. The next one's 2 times 0, 2 times 1, 2 times 9. But I'm just going to factor out that 2. All 4 rectangles have the same base, and that's delta x, which equals 2 here. And then I'm just going to add up my 4 heights. 1 plus 0 plus 1 plus 9. So in the parentheses I have 10 plus 1 is 11 times 2. This is 22. That's the area of those 4 rectangles, and that gives me an approximation for the area of the yellow shaded region, and we can tell by looking that this is going to be an underestimate. In fact, it's by definition of lower sum. We're taking the lowest possible heights. This is always going to give us an underestimate of the actual area. So let's now do the upper sum, part B. Same idea, but instead of using the smallest value on each interval, we're going to use the largest, and so we're going to get an overestimate this time around. And so what this is going to look like, the first interval from 1 to 3, there the high point occurs on the left side at 1. So f of 1 will give us the height of this rectangle. And I'm going to use a different color here. I'll use red again. So the height of this one's f of 1, but that's going to be 9 from our table. That's the first height. The second one has a height of, in my picture it's not clear. Is it f of 3, f of 5, which one's higher? But I can see that in my table those both have the same height. It's 1. So I'm going to use the height of y equals 1 for my second rectangle. That's both f of 3 and f of 5. For my third rectangle, the tallest height is f of 7. That's going to be 9. And the fourth rectangle over on the right, that's going to go all the way up to f of 9. So I'm going to use x equals 9 there for my x value. And same idea. So now the 4 heights of these 4 rectangles I've put in red now are 9, 1, 9, and 25. So I can just go to my formula. It's base times height for each of these 4 rectangles added together. But again, I'm going to factor out that base. That's delta x, which is 2. The base of each rectangle times the height, which is 9 plus 1 plus 9 plus 25. 25 plus 9 plus 1 is 10, so that's 35, and 9 is 44 times 2. Looks like this gives us 88. So this is a big discrepancy between these two estimates, but we can tell from our picture why that is. One is a big underestimate, the lower sum, which gave us 22, and the other is an overestimate, the upper sum, which is 88. If I want to be more accurate to get to increase the lower sum, decrease the upper sum, we could use more intervals. The more intervals we use, the more accurate we'll be. And another thing we could do is use the midpoint rule, which kind of splits the difference. So the midpoint rule, let's look at this one, part C. The midpoint rule says, if I'm looking at the interval from 1 to 3, I would use the midpoint to determine the height of that interval, which is would be f of 2 in this case, or f of 4. So instead of using the highest or lowest value, I would use the midpoint, whether it's high or low. But let me read the question here. Part C says we're only using 2 rectangles now. So that's going to change things. We're now just going to have 2 rectangles. And so that's going to change our value of delta x in part C. So again, I'll calculate it. I'm going from 1 to 9. So I'm going to start in the numerator by taking 9 minus 1. That's 8. That's the length of this interval. And now I'm just going to divide by 2 because I only have 2 rectangles in this part of the problem. So 8 divided by 2. So my delta x now is 4. I have 2 rectangles, each of width 4. My picture is getting a little bit messy now, but my first interval will go from 1 over to 5, because that's 1 plus 4, and then plus 4 again. So my picture doesn't look symmetric. It should be. Again, this wasn't drawn to scale. But this is the idea. The first, we're going to have 2 rectangles. The first one goes from 1 to 5. The second one goes from 5 to 9. And to determine the height of each of these rectangles, we're going to use the point in the middle. We're going to use x equals 3 for the first interval, x equals 7 for the second interval. So I'll highlight these in the table. So we're using 3 now and 7 for the midpoints. So for the midpoint approximation here, we're going to use the heights 1 and 9. And that's going to give us, so again, same idea. We're going to have 2 rectangles. The area of a rectangle we know is base times height. In this case, the base of each of the 2 rectangles is 4. So I'm going to have 4 times the height of the first rectangle plus 4 times the height of the second rectangle. I'm just going to factor out and say it's 4. And I'm going to look at my table, 1 and 9. 4 times 1 plus 9. And that gives us 4 times 10, which is 40. So, and we shouldn't be surprised that this approximation is in between the previous 2. The downside with this approximation of 40, I'm not sure if it's an overestimate or underestimate. I know 22 is an underestimate, 88 is an overestimate, and the third approximation, using the midpoint rule with only 2 rectangles, gives us an estimate of 40. And if we wanted to get a better estimate for the area of the yellow shaded region, we could just do this, follow the same process with more and more rectangles.